were awake an hour earlier than you were when the first day
All right. Good afternoon. Today we are going to finish Mohr circle by covering some examples and study Mohr circle, and then we are going to start the beam as the first mechanical component that we're covering in this course. So you have seen beams on strength of materials, but we are going to have a review of that. So any questions before we start? Alright. So we learned about the Mohr circle if we are given with a stress element, plane stress element like this. You can pick point A and B and write the coordinates of point A, which is located on this plane, as a term of normal stress and shear stress. If the normal stress is tensile, it's going to be positive. If the shear stress for counterclockwise, it's going to be negative, and for clockwise, should be considered positive. So it's making counterclockwise rotation in this plane, so it's going to be negative tau xy. B is going to be sigma y, positive tau xy. Then locate point A and B on the plane on x and y axis, which are sigma and tau, and then draw the Mohr circle. These 2 points would be principal normal stresses, and this is P 2 phi p, sorry, which is representing principal normal stress direction. Yes.
I just had a question about how you determine that angle, because for the homework, sometimes it would be like the opposite angle. So I know, like, one of them I had right here. I think it was 40 degrees. It was 80 degrees, maybe something like that.
Mm-hmm.
And just for an example, let's say 80 degrees. So half of it was 40, but it had like 280 was the other way divided by 2.
Which is 90 plus.
Right. So is that okay?
Again, yes, it's okay as long as you are consistent. So
Okay.
if you can see I can rotate this by this angle, or I can rotate this by this angle.
Okay.
Which is 180 plus 250. Half of that is going 90 plus 50, as you said.
Okay. I just wanted to make sure, because I wasn't sure, like, if you had to negate it then or what. So as long as you label it.
Yeah, if you label correctly and consistently, yes, you should be good. So if, for example, if you represent, for example, 40 degree, which is 2 phi p equals to 80, then you should say it's gonna be positive, whatever is this value. But I mean, suppose this is 110, this is 20. But if you represent 80 plus 90, 40 plus 90, then this guy is gonna represent 20. Yeah.
Oh, okay.
Makes
I
sense?
see what you mean. So you got to make sure you get your arrow.
This is what I mean by consistency. So the angle should be consistent with the corresponding angle.
Okay. I might have to double check that then. Okay.
Yes.
So in that example, if you rotated A clockwise to the left part,
This can be possible.
that's allowed?
It's allowed, but you should say, all right, I'm gonna rotate this and represent the angle with the negative value. So you can say I'm gonna rotate by 80 plus 180, which is 2 pp. 80 plus 180 if this is 80. Or you can say I'm gonna rotate negative 100, which is gonna be which is gonna see point A at this position.
So wherever point A ends up, whichever position that's the number that the side that A came from now has on it.
Yes.
Okay.
Yep. You just look at point A and B. Where are they now? So if you rotate this AB by this angle, what is the value for stress at point A? It's gonna be 110. How much did you rotate that? A half of AD, which is positive 40. So you rotate it by the angle of 40. So point A is gonna be here, point B is gonna be there, and A is gonna see 110, if this is 110. Point B is gonna see 20. If you rotate by half of this, then point A is gonna be B, point A is gonna be 20, and point B is gonna see 110. Okay. Any other question?
On the for the eigen, the question 20, the answers are in the back of the book, and the eigenvalues I got weren't the values in the back of the book.
Okay.
I don't. Is there something other than just doing the eigen that should just be it?
That's. I mean, I'm gonna cover eigen today shortly,
Oh, okay.
but you should get the same things that you got on the back. Sometimes the answers are different because there are some mistakes on the answers on the back of the book, but eigen is eigen.
Okay.
There is nothing surprising.
Yeah, if you're going over it today. Then.
It's gonna be quick because we don't go in detail. So, any more questions? All right. So, this is what we covered so far. Now, if you are given with a stress element which has principal stresses, sigma x and sigma y. Since I don't have any shear stress, these values are principal normal stresses. How do I know that? Because there are no shear stresses here. So point A, point B. Sorry guys. So for point A, the coordinate is going to be sigma x, and there is no shear stress. For point B, it's going to be sigma y, and no shear stress, which is going to be 0. I assume that sigma x is greater than sigma y because I would like to locate point A and B. I make this assumption. This is sigma x, this is sigma y. So this is going to be the center, and this is going to be the Mohr system. Now, if I ask you, and point A is going to be here, point B is going to be there. Now, if I ask you, what if I would like to rotate this by the angle of theta, or if I want to cut it by the angle of theta, what would be the new normal stresses and shear stress applied to the stress elements? We are going to use the same thing. We are going to rotate line AB by the angle of 2 theta in counterclockwise direction. So suppose it's going to be here, point A is going to be right here, point B is going to be there, and this angle is 2 theta. We are looking for this as a sigma prime x, this as a sigma prime y, and this then as a tau xy, which are the coordinates of normal and shear stress for point A and point B. So what would be this? It's going to be center plus, if this is r times cosine of 2 theta. So sigma prime x is center plus r cosine of theta, 2 theta. R cosine of 2 theta is going to be this time plus the center. It's going to give me sigma prime x. What would be the center? Summation of these two. It's going to be sigma x plus sigma y divided by 2 plus r. R is AB divided by 2. AB divided by 2 is going to give me the radius. And AB is sigma x minus sigma y divided by 2. Sigma x minus sigma y divided by 2. So this is going to look like this. So the value of sigma prime at plane which has point A located on that is going to be sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cosine of 2 theta. Same thing for sigma prime y. Sigma prime y is going to be the center minus this distance. It's going to give me sigma prime y. Center minus r cosine of 2 theta. R cosine of 2 theta. Just change this positive to negative, you will get sigma prime y. And what is the tau xy? It's a r sine of 2 theta. And r is right here, sigma x you will get any question on this? In this slide, you can see the result, sigma phi, which is this guy, it's going to be sigma 1 plus sigma 2 divided by 2 plus this term, and shear stress is going to be r sine of 2 phi that I have already. Alright, let's work on some special cases before we move on. 3-dimensional Mohr circle. Suppose the stress element that we have here, it has the same principal normal stresses of sigma 1, sigma 1. They have the same value. Since they are principal normal stresses, we don't have any shear stress. For example, 10 megapascal and 10 megapascal. We would like to draw the Mohr circle. For point A, the coordinates are positive 10 because it's tensile stress and no shear stress, 0. For point B, same logic, positive 10, no shear stress. Then you need to locate point A and B. If this is 10, point A is going to be here, point B is going to be at the same location. because they have the same coordinates. Now, if you connect point A to point B, since they are the same point, the length of AB is going to be 0. So the radius is AB divided by 2. You are going to get a circle with the center of 10 and the radius of 0. Any question about it? All right. The principal direction, since it's already principal normal stresses, we don't need to rotate this. So it's going to be phi equals to 0. What would be the principal shear stress? Principal shear stress. You know that these two angles, the difference between these two angles is 45. So phi s is going to be 45 degrees. So if I rotate this by the angle of 45 degrees, I will get principal shear stresses. You remember, if I have a full Mohr circle, what would be the maximum, the extreme value shear stress is going to be here, which is going to be positive R, and the other extreme is going to be negative R. So the shear stress, extreme shear stress is going to be positive R, and R is 0. So there is no shear stress right here. And at this location, what would be the normal stresses is going to be the center. The center is sigma x plus sigma y divided by 2, which is 10 plus 10 divided by 2, which is 10. So I will get 10, 10. So although you rotate it by the angle of 45 degrees, since we have the same value for the normal stress, principal normal stresses, we don't see any shear stresses. Here we only see the same value of principal normal stresses. So this is one special case, and it's because both principal normal stresses have the same value. Now, as a class activity, draw the Mohr circle for this stress element, which has only pure shear stress.
Dr. Rafi?
Yes.
What does that equation say? I can't read it from here.
This is just how XY is positive 10 megapascal. The shear stress, pure shear stress, has the value of positive 10 megapascal. Means the arrow in this plane should go up, and arrow in this plane should go to the right. Draw the Mohr circle and find the principal normal stresses. Is that clear?
That's just what maybe that helps with this.
Hey, Michael. What do you think? I mean, would you come to the board and just start from writing the coordinates of point A and B, then
Sure.
you go? Thank you. Point A is gonna see the positive 10.
Right.
Number 47.
I think C and A are switched.
A and B. This one is correct. Point A doesn't have any normal stresses, so it's gonna see 0. But for the shear stress, is making rotation in this direction. It's making rotation on this square in counterclockwise, and in Mohr circle, counterclockwise is negative. B doesn't have any normal stresses, but this one is making rotation in opposite side, which is clockwise, and it's going to be positive 10. So point A is going to see negative 10 and 0 and negative 10. Point B is going to see 0 and 10. The principal, any question on this? So for principal normal stresses, this is line AB. If you rotate, you can rotate either in counterclockwise or clockwise. I rotate in counterclockwise. So point A is going to see this location, and point B is going to see this location. Sigma prime 1, sigma prime 2, or B prime and A prime, just to locate point A and B. Okay. So this line is representing the principal normal stresses because there are no shear stress. What would be the angle? Positive 2 phi is 90 degrees. So phi is going to be 45 degree positive because we rotated counterclockwise. So if I rotate this by the angle of 45, point A is going to be here, rotating. Point B is going to be on this line. Point A is going to see this value, which is equals to the radius, half of AB. AB is going to be 10 plus 10 divided by 2. The radius is going to be 10. So the magnitude is going to be positive 10, sigma prime 1 is positive 10, and sigma prime 2 is going to see the negative 10. which representing compressive stress. If you want to rotate in this direction, point A is gonna see this one, -10, point B is gonna see +10. The rotation is gonna be positive, negative 45. Just rotate in clockwise. Positive 45. Negative 45 degrees. Point A is gonna be here. Point B is gonna be up there. If I rotate it clockwise, 45 degrees. Point A is gonna see negative 10, and point B is gonna see positive 10, which is exactly same as this one. See, in this plane, in this line, it goes up. In this line, or in this plane, it goes toward the plane. So these are some special cases for Mohr circle. Any question about this? Alright, before I move to the 3D Mohr
I
circle,
had a question.
sorry.
Just when I was doing the homework, the book likes to give its starting, like its A and B positions with rotations. So it'll just say like 8 KSI clockwise. How do I translate that into the little box, the plane drawing? Which of the arrows are they talking about when they say clockwise?
This one.
Okay, so it's always the right-hand side one?
Yep.
Okay.
If I say the shear stress is -10, it tells you it should be clockwise in right plane, in this plane. So just draw a shear stress pointing down to make it clockwise.
Okay.
And then after you figure out this, you can find the other arrows directions. It goes opposite direction, it goes up, and it goes to the left.
Okay.
So everything back to the display, right side. Good question.
Thank you.
All right, before we move to 3D Mohr circle, let me practice what we learned on Thursday class. So the normal stress, principal normal stress is +10, the other one is -10. The third principal normal stress is 0, as always. So you can rank them as a sigma 1 greatest, sigma 2 the middle one, and the sigma 3 is the smallest one. Sigma 1, the greatest, is +10. Sigma 2 is, the middle one is -0, and sigma 3 is gonna get -10. So sigma 1 is +10, sigma 2 is 0, and sigma 3 is -10 megapascal. It's the reason that I had the prime here. I didn't say sigma 1 and sigma 2 because I don't know. I should rank them before I label them as a sigma 1 and sigma 2. And if I ask you what would be the maximum shear stress, it's always this difference is going to be the greatest. Sigma 1 minus sigma 3 divided by 2, which is 10 megapascal. All right. So as you see, when we talked about the Mohr circle, we talked about plane stress elements. But what if we have a general stress element with 3 planes?
Two classes.
Something like this. If we have a general state of stress which has 6 terms, how can we find the principal normal stress of sigma 1, sigma 2, and sigma 3? I don't go in depth, I just write the equation that you can get, the principal normal stresses for a general state of stress element. So the terms that we have are sigma x, sigma y, sigma z, tau xy, tau xz, and tau yz. 6 terms. So to find the principal normal stresses, you should find the roots of this cubic equation. So if you look at equation 315, it's a cubic equation, sigma cubic, sigma square, sigma, and this is a constant part. You may get 3 roots for that. Sigma 1, sigma 2, and sigma 3. These 3 roots, they are going to be the principal normal stresses for this state of a stress element. So this is one way that you can do. The other way is finding the eigenvalue of this matrix. Sigma x, whatever its value, put it there. Tau xy, tau xz, just put the value in the matrix form and try to find the eigenvalue for the matrix. If you have taken the linear algebra, you are familiar with the eigenvalue and eigenvector. But if you have not taken, that's okay. You just, in MATLAB for the homeworks, type EIG inside the parentheses, put the matrix form. So here in MATLAB, for example, sigma x is 25, tau xy is positive 10, tau xz is negative 5, tau y is 15, tau yz is negative 10, and sigma z is negative 20. Just enter the numbers in the matrix. Matrix A is going to be sigma x is 25 space.
Put all tau xz top of
This one. Tau x equals to tau zx. Did I forgot? Okay. Tau xz. Thanks. and negative 5 is tau xz or zx, the same. Second row, semicolon, tau xy is 10, tau y is 15, and tau y is negative 10. And last line is negative 5, negative 10, and tau sigma z is negative 20. If you just type EIG of the matrix A, you will get 3 answers. So these are the principal normal stresses. Sigma prime 1 is negative 22.77. Sigma prime 2 is 9.8. And sigma prime 3 is 32.9. So if you rank them, sigma 1 should be the greatest, which is 32.9. Sigma 2 is the middle, it's 9.8. And sigma 3 is negative 22.77. This is how you can find the principal normal stresses by using the eigenvalues. Make sense? Now, if I ask you to draw the Mohr circle for the plane stress, you can do that for this one. You know how to do this. But for three-dimensional, first of all, you can locate sigma 1, sigma 2, and sigma 3 on the axis. Sigma the sigma 1 is 33, almost 33. Sigma 1. Sigma 2 is 9.8. Somewhere here, and sigma 3 is negative 22. So between each two principal normal stresses, draw a circle. Sigma 1 and sigma 2, you can connect them and draw a circle. Between sigma 2 and sigma 3, you can draw a circle. Between sigma 1 and sigma 3, don't forget to draw a circle. Something like this. So you will get 3 circles because you have 3 combinations between sigma 1 and 2, sigma 1 and 3, and 2 and 3. If I ask you what would be the maximum shear stress, you can say, I'm going to look at the largest circle or greatest circle, and the radius of that circle is going to give me the maximum shear stresses. The largest circle is going to be this. The radius of that is going to be sigma 1 minus sigma 3 divided by 2. Good? If you have a plane stress element like the previous example that we did, one of the principal normal sources always would be 0 because we have plane stress. For this one also you can draw 3-dimensional Mohr circle. Sigma 1 here it's 10. In this example sigma 2 is 0 and sigma 3 is negative 10. Connect 0 to 10, draw a circle. Connect 0 to minus 10, draw a circle. Connect 10 to negative 10 and draw a circle. Again, you will get the 3 circles. Just one of the values is always 0. On MDT toolbox that I have on left side, can you see the left column? I mean back there. One of the M files name is Mohr 3. This guy, Mohr 3. For this one, if you just type Mohr 3 parentheses and enter the 3 value of sigma 1, sigma 2, and sigma 3, it's gonna draw the Mohr 3-dimensional Mohr circle for you. So sigma 1 is 32.93 in this example. Second one is 9.8, and the third one is negative 22.77. So it's gonna draw these 3-dimensional Mohr circle. You can see, you can read the numbers, but it's gonna tell you what would be the maximum shear stress in this circle, and in the larger. Good? So that's all you need to know about the Mohr circle. So let's start beams. As the first mechanical component that we covered in this course. There are different types of the beam. We have simply supported beam, like this. Or you might see the cantilever beam. Something like this. So the beams can be under concentrated load like this, F1, F2, these are concentrated load, or distributed load, like this. If you put a weight on the top of the beam, it's gonna be an example of distributed load. Same things here. We can have distributed load and some concentrated load. These are just review. So for concentrated load, we are using a term of Q, which is the load divided by M, which is the density of the load, so we usually represent this with, for example, Q is 50 Newton per meter if the units are in SI. In US system, it's going to be inch. Depending on this length, we can calculate Q. If you remember, the first thing that we defined on this course was critical section. This is the first mechanical component that we start working on that, and we would like to find the critical section for a given beam with the load applied to that. So what do I mean? I would like to find at which section of this beam, at which location of this beam, I will see the largest amount of the load. So which section is going to be that one? Or if the failure occurs, at which section is going to happen? This is the definition of the critical section. So we would like to find the critical section on the beam, and then critical point. Suppose I did the analysis and I could find that at this location, which has the distance of L1 from this point, I'm gonna have the critical section. If the cross section is this rectangular, I would like to know at this critical section which point of this cross section is gonna see the largest amount of the load, and the failure is gonna occur at that point. So this is the question that we would like to answer. So critical section first, then critical point. This is very important because we are gonna do it for all mechanical components that we cover in this class. All right, let me stop here and continue on welding.